Our June edition of the Cause Activity webinar. I'm Lee Johnson. I've hosted these in the past. So for those of you who are big Hunger Games fans, we are talking with Kyle Caudle today. I do want to remind you that there's about 20 minutes of presentation. If you do have a chat, or I'm sorry, if you do have a question or you're having some technical issues, feel free to type in the chat window. But we will try to leave content questions until the end of the presentation. So please be assured if you do put a question in, it will get asked, it will get answered. But we might let that go till the end of the presentation. So, Kyle, I'm going to go ahead and let you take it away.
Okay. Thank you very much, and thanks for inviting me to do this. As Lee said, I'm from South Dakota School of Mines and Technology out in western South Dakota. We're almost in Wyoming. And I'm here to give you kind of an overview of an in-class exercise that you might use to teach randomization tests. And as the title indicates, it's based on the data from the Hunger Games. So if you've read the books or seen the movies, maybe you'll recognize some of the things that I'm going to talk about during my webinar here. So let's see. So a brief outline. I'll give you some background in case you haven't read the books or seen the movies, which probably not too many in the audience, I would guess, that are at least a little bit familiar with the Hunger Games. Go through an introduction, and then I'll talk about randomization tests and kind of work through a first example, kind of a simple way to introduce you to randomization tests if you're not familiar with that. And then we'll get into the kind of the meat of the presentation, which is a permutation goodness of fit test that's analyzing the lottery data that comes from the book The Hunger Games. So some background here. This project was actually a joint research project that I worked on with one of our senior math majors. Our senior math majors are all required to do some sort of research project, studying something that is not necessarily new research, but new to them. And Erica wants to be an actuary, so I thought, well, we could look at some survival analysis. So the bulk of her research was actually looking at building a survival model to see how long people survive in the arena. And as kind of an aside, we analyzed the lottery, which is how students are chosen, or students, excuse me, how children in the book were chosen to participate, for lack of a better word, in the Hunger Games. And so that's the focus of this talk, not the survival analysis. This portion of the research, we decided to write a teaching journal article, and it was published in Teaching Statistics last summer. And I guess they really liked it because they gave us the Teaching Statistics Peter Holmes Prize for the best classroom activity last year. And it seems to have some legs. It was republished in a German journal earlier this year. So, and then I got invited to do this. So we were pretty pleased that it's gotten as much traction as it has. So for those of you who don't know, the Hunger Games is an annual event in a fictional country called Pan Am, loosely based on kind of the United States after some sort of huge war. There are 24 children called tributes that are chosen by lottery from each of 12 districts and they have to, unfortunately, they fight until there's only one person left standing. It's kind of a little on the gruesome side. And so we looked at the lottery and how these children were chosen to fight in the Hunger Games, and tried to decide whether or not the game makers, those who are actually in charge of running the Hunger Games, we wanted to analyze that and see if maybe they were rigging the lottery. So like I said, there were 2 children chosen from each district. There were these other children that train exclusively for the Hunger Games, and in the book they're called careers. They're not chosen by lottery, and they may volunteer for the games for one of the children that actually got selected by the lottery. So as you'll see, they're not part of the analysis because they volunteered and were not selected by lottery. Katniss, who's the heroine of the story, she volunteered for her 12-year-old sister, so we use her sister's age, 12 years old, and not Katniss's age. And so the way the lottery works is when you're 12 years old, you get 1 ticket in the lottery, and if you're not chosen, the next year you get another ticket plus the one that actually didn't get drawn the previous year. And so this continues until you're 18, and at which point, if you haven't been chosen yet, you'll have 7 lottery tickets in there with your name on it. And there's another added kind of monkey wrench, so to speak, which is called the tesserae, which is basically where you can get an extra ration of food for your family if you agree to put your name in the lottery an additional time. So if you kind of look at those proportions, you can specify kind of the proportion of entries in the lottery at any given time by age. So there should be, roughly 1 out of every 28 entries belonging to a 12-year-old, and so on and so forth, up to 7 out of 28 for 18-year-olds. So these are kind of the theoretical proportions should the game makers actually be following the lottery rules. So that's what we want to know. Based on these proportions, do we believe the game makers are actually following the lottery rules? Okay. I mentioned that there's this thing called the tesserae, and the book is actually pretty void of details as far as the tesserae goes. They just mention that that a child may take an extra entry in the lottery in exchange for food for their family, and so and that's pretty much the only details that the book gives. So we sat down and we said, well, what might be a reasonable or a modest assumption regarding the tesserae, since the book didn't mention anything, and we decided that maybe the younger kids would not exercise this. Essentially, we thought, well, why would that be? Well, maybe because they're younger and they're not as hungry yet. They haven't gotten into that adolescent age where they consume a lot more calories. And also, we figured the older children are now becoming more responsible, and they would feel kind of a sense of need for their family, and therefore we thought maybe the 16 and 17 and 18-year-olds would exercise this right, and so it changes the proportions a little bit. So you can see in the table there, based on these modest assumptions, what the proportions would now look like. All right, so what's a randomization test? Basically what you're doing is you're looking at what could happen if you ran an experiment a large number of times, simply put. And so if you read the article, and I'll introduce kind of an introductory example here as well, let's assume that Katniss, the heroine in the story, and her friend Gale, another character in the story, let's assume that they go squirrel hunting, and they come back with 4 squirrels on a particular day, and it turns out that Katniss killed all 4 of them. Okay, so we're making that assumption. We would like to test the theory that maybe Katniss is a better hunter, and how much better is she? Well, we're going to test the theory that she's actually twice as likely to kill a squirrel as her friend Gale. So, is that a plausible assumption? So how might we go about testing that in kind of a classroom setting? So the way we propose doing this is take a set of regular index cards, and on 3 of the index cards write the name Katniss, and on 1 of them write the name Gale. So you have this deck of 3 cards that you can now draw from to simulate killing a squirrel, and it's set up so that Katniss here is twice as likely. She has 2 cards to Gale's 1. So what you could do in the classroom then is you could pick on some students, and you have them draw 1 of the cards out of this deck. And if it comes up Katniss, then that's saying that Katniss killed the squirrel. And then you replace the card back in the deck so that it's back to its original configuration, and then you redraw until you've killed 4 squirrels. So at that point you'll know of the 4 squirrels how many Gale killed and how many Katniss killed. Now, because this is such a simple example, if this is an introductory statistics class, you've probably talked about counting and how to count all the possible things that could happen. And it's not too hard to calculate that if there are 3 choices and you do it 4 times, that would mean that there are 3 to the 4th power, or 81 different outcomes that could happen. And so, well, how many of those represent that Katniss kills all 4? Well, there's only 2 ways out of 3 that Katniss can kill. Both can kill a squirrel. So there are 2 to the 4th ways, or 16 ways that Katniss can kill all 4 squirrels. So if you take that 16 and divide it by 81, you get roughly 20%. So there's about a 20% chance that Katniss will kill all 4. So my recommendation when you're doing the cards and you're having the students draw the cards is make sure you do this 5, 6, 7 times, so that at least one of the students, at least in theory, at least one of the students will arrive at a situation where Katniss kills all 4 squirrels. And then you can, entertain the students in a discussion of, well, hey, we actually saw this happen. So, and the assumption was that she's twice the better hunter that Gale is, and you can kind of get them in a discussion, hopefully, as to that, yeah, it's pretty plausible. About 20% of the time, if Katniss is twice as likely to kill a squirrel, it'll turn out that she kills all 4. So that's kind of a basic randomization test. When it comes to the lottery, we can't actually draw all possible lotteries. One, we don't know how many kids there are in the country of Pan Am, and the book doesn't really tell us much more than just kind of the proportions that would be there. So, so we decide to actually kind of do another simulation, or simulation rather. So, in the book, if you get rid of the careers, you see that there were 17 children chosen by lottery, and the book actually tells you exactly how old each of the 17 children were. So we get the actual counts. The bar graph there shows you the actual, and then if we multiply those proportions by 17, we get the expected counts. So then you can show the students this plot here, and you can say, well, what do you think? Do the actual counts, are they kind of in line with the expected counts? So, like I said, we can't look at all possible combinations, so make yourself another deck of cards. In this case, you'll need 28 cards to match the proportions in the first table that I had. One card gets the number 12 written on it. You put 13 on 2 of the cards, 14 on 3 of the cards, and so on and so forth until your deck of 28 cards exactly matches the proportions in that first table. Then you have the students draw a random sample of size 17 from this deck, again returning the card after each pick so that it's returned to its original configuration. And then you can get into maybe somewhat of a good discussion here on okay, well, how many 12-year-olds would we expect to have in our sample of size 17? How many 15-year-olds? How many 17-year-olds? And see how that kind of works out, and get the students thinking about the kind of things that would happen if we draw from the theoretical distribution. And so then we get to a point where we say, well, yeah, we kind of expected one 12-year-old, but we only got 2. Is that close? How do we measure closeness? Okay, so in some of my classes, I actually get to a chi-squared goodness of fit test, but I point out here that the assumptions aren't met for a chi-squared test because your cell counts are kind of small. But we can still use the chi-squared test statistic, if you're familiar with that, as kind of a measure of how close we are. So we just take the observed count and we subtract the expected count. Could be positive or negative, so we square it, and then we roughly standardize it by dividing by the expected count. And then we add them all up for each of the age categories. So then we get a number. So the question is, well, is that a big number or is that a small number? Okay. So we look at the book data and we perform this calculation and we get 9.11. So when you have your students draw their sample of 17, have them go through the exercise of calculating this test statistic and kind of entertain another discussion. How many people got a test statistic that was bigger than the one in the book? Okay, what would you think? Would you think that we're close enough to 9.11 to kind of believe that maybe the game makers are doing the right thing, they're following their rules? But you know, again, it's kind of hard because you're only gonna. It's going to take a while to draw a sample of size 17 with the index card. So, and you're only looking at maybe a half a dozen of these, but it's a good place, good starting point for discussing. Hey, are these actual counts? Are they close to what we would expect? So, what we'd like to do is we'd like to run this thing thousands of times, 10,000 even. Okay, now you're not going to have the students draw from that deck 10,000 times. So if you're familiar with R software, I have written an R package that will actually run a simulation. It will simulate in a matter of seconds drawing from this theoretical distribution thousands and thousands of times, and then it will calculate the test statistic, and it will keep track of how many times our simulation arrived at a test statistic that was larger than 9.11. So I've got two links there for you. You're welcome to, if you're not familiar with R, there's a brief tutorial in the manual on how to run the package. And you may have to either email me or get with someone if you're not familiar with R with regards to how to load a package, but the package itself is on that first link. And you can actually run this command that I showed there, rtest-hg, and it will run the test m times, whatever number you put in for m. So it will run it thousands of times. And you can analyze this both ways, either using our assumptions for the test array or not using those assumptions. So here are 3 times that I ran it when I was getting ready for this webinar. And this first case here are those that do not include any assumptions for the test array, just using the first table that I showed. And it turns out that about 15% of the time, just due to randomness, I get a test statistic bigger than 9.11. So you could ask the students, what do you think? Do you think the game makers are rigging it? I would argue that probably not. 15% is a pretty large number. That's actually, if you're familiar with hypothesis testing, that's actually a randomized, what we call a p-value. Not to get into the technical details of that, but that's a p-value. And a general accepted cutoff is anything less than 5% makes us question our assumptions. But again, there's nothing really sacred about 5%. But 15% seems a little high to think that maybe there's anything going on with the game makers here. And then on the next slide here, I have where I looked at the test array distribution, and hey, you know, it's less likely that using those assumptions that you're going to get a test statistic bigger than 12.55, which is, you know, what would happen if you actually made those assumptions. And so now we're kind of getting into the realm of, hey, you know what? Maybe there's something funny going on. Now, we made up the assumptions for the test array, so, you know, because the book was void of details, but maybe there's something going on. It's not really that likely to get a test statistic of 12.5, 12.55 or higher. So anyway, this is an interesting exercise just to get students to start thinking about, you know, if I did something a large number of times, what would happen? What conclusions can I make when I look at what would happen in the long run? So conclusions, essentially, I like randomization tests. I mean, it's not something that I was able to do when I first took a statistics class back in the 80s. Computers weren't well, there were computers that would probably do it back then, but it wasn't readily accessible like it is now. And I think simulations and simulation-based inference is really kind of where we need to go in the classroom setting. I think just getting an intuitive feel for what could happen when you run an experiment a bunch of times, you know, roll a pair of dice thousands of times. I mean, all that is definitely manageable now. And again, I think the biggest takeaway for me on this is, hey, when you mix pop culture with statistics, it really excites people. It excites students. It makes their learning more enjoyable, and I had a lot of fun working through this with my student, and hopefully she learned a lot, and I learned some, and it was a good time. So, subject to your questions, that's all I have.
All right. Thank you, Kyle. That was great. We did get a couple of questions. One was just kind of a technical question. The R links that you had,
Yeah.
We can't click directly on those right now. Is there a way to link them directly in the chat window, or will they be on the slides later?
Oh, they're not. It's not working. Oh.
No, it's
Um,
not something that we can click on. You can on your computer. Um,
oh.
but
So, what do you think the best way to handle that is? Should I put it into the chat window? The
I don't
links?
know if that would work at all. I'm not familiar with the R links. I think we are going to post the slides themselves,
Okay.
after the
So
talk's over. So,
what I could do is give you an updated version of the slide with the actual written out link, if that might work better.
yeah, or I mean, I know some people are asking. Hold on, Ruth. That will work. Okay. So, yeah, I mean, if you can just put those links in the chat window if anybody wants them right now, and then maybe put them on the slides as well for when we post them.
Okay. Let's try that real quick. So that's the link to the package, and then the documentation is right there.
Okay. Yeah, that should work.
Okay, excellent.
So it should work the way you have it when we post the slides. It's just because we're all in a different. It's not a PowerPoint
Oh, yeah.
application that we're in right now. There were a couple questions about the tesserae.
Uh-huh.
So Tracy asked, on page 13, chapter 1 of the book, it describes the process about the tesserae. She's questioning the assumption that you made. You can claim tesserae for each family member once a year. So it says that Katniss at age 16 has her name entered 20 times. Gale, who supported a bigger family, has his name in 42 times at age 14. Could you use that data to make your assumption a little bit more in keeping with the book?
Yeah, probably. I'd forgotten that when I read the book. Um,
Okay.
yeah, but that's an interesting point. In fact, um, boy, my rough thought on that is if you did, change those proportions, weighted the older proportions much higher, you might even get a smaller p-value. So we just tried to make some real modest kind of what would happen over the grand scheme of things, because the richer kids probably wouldn't exercise the right for the tesserae, but you know, Gale and his family, and Katniss and her family, they were on the poor side, so maybe their higher proportions wouldn't be in keeping with the overall population, but that's an interesting thing to think about.
And the other question, this was just sort of a what if, have you run it with the assumption that the 12 to 14-year-olds actually would take the tesserae because their parents figure out they're less likely to be chosen at a tribute at this age, and so, um,
Ah,
you know,
no, I haven't. But
counteracting the.
yeah, you could counteract the fact that they don't have a lot of entries to begin with. That it might. Ah,
I think you have to.
interesting. I mean, again, uh, the book doesn't have a ton of details, so um,
Yeah.
you're kind of flying by the seat of your pants, sort of.
And Don Davis asked, how can we best access students' knowledge? This is sort of more of a general question. Access students' knowledge of randomization tests and simulations. Do you suggest projects, tests? I'm sorry, that should probably be assess students' knowledge of randomization tests and simulations. Do you have any suggestions on how you assess their knowledge?
Um, I don't have a good way of doing it on an exam, so
Okay.
if anyone has an idea of how to test this on an exam, I'd be all ears for that. Projects, sure. You could you could ask them to run an experiment. I have my students do projects, and part of that project they actually have to collect data, and some of them who pick gambling related things, like I had a student project team study how many times you have to shuffle a deck of cards in order to make it random. And so they actually did that a whole bunch of times physically, and then they wrote some code to do it. They happen to be computer science majors, so that was an interesting project. But yeah, I think as far as testing randomization stuff, it's pretty hard to do on an exam. Now, I have used the Rossman Chance applets. I let my students use their computer for R, and one time I did let them use, so Beth Chance and Alan Rossman have this set of applets on the web, and one time I let my students actually do that randomization on an exam, and then I asked them some questions about that. So that was it was okay. I haven't done it since because I wasn't particularly pleased with the way it worked out. But yeah, testing it on an exam would be kind of a challenge.
Okay. Your students have a basic knowledge of R, or do you pretty much give them the code?
I don't expect them to write any R code.
Okay.
We use R and the built-in R functions. If I'm going to ask them to do a randomization, I write the code for them.
Okay. Okay. All right. Well. Oh. Okay. Okay, there was a suggestion from Ruth. I don't know if you want to comment on this. Ask them how they would model the null distribution without technology. Give them a simulation and ask them how they would use it to assess the strength of the evidence against the null. Ask them what an individual dot in the simulated null distribution means. And I think if you've used, if you've seen the lock book, lock, and lock, some of the questions that they have in there, they do that sort of thing. So you don't actually run the simulation, you give them the results, and then students have to explain what all the different pieces are.
Sure.
So, and I've actually put a couple of those questions in my tests, and they seem to work pretty well, because I've used a lot of simulation stuff myself, too. So, I don't know if you wanted to comment on that.
No, I don't use that book, but that sounds sounds like an interesting way to be able to test that.
Yeah.
But I don't really have any thoughts on that.
Okay. I may have said one too many locks. There's like 5 of them. Well, I think that's all our questions. So, Kyle, thank you very much for doing this. This was really very interesting. And you said the article's published in Teaching Statistics. So if you want information beyond the PowerPoint, you can look up the article as well.
And do you have my email address down anywhere?
Yeah. Oh, for everyone?
Yeah.
I do not have it ready at hand. If you want to just go ahead and post it in the chat window for people.
Okay, because if they have any troubles with the R package or anything, they can certainly email me.
Okay. So yeah, we'll just hang on here a minute if anybody wants to.
Did it go through?
Yeah, I just want to give everybody a minute if they wanted to copy that.
Okay.
All right. Otherwise, I hope everyone has a very nice afternoon. Thank you again, Kyle.
All right.
And I'm sure we will see all of you soon again.
Okay. Bye now.
Bye.